Welcome everyone. I'm videoing from my front yard where as you can see we got a little snow last night. Today's lecture will be on the differential analysis of heat transfer. So I will derive the heat equation. So if you guys will, come inside with me where it's warm and we'll get started. Okay, welcome back everyone. I'll start today's lecture by asking a question. What if you wanted to know the temperature in a material at any location X and Y in that material? Well, to answer that problem, you would have to resort to differential equations, and that's what we'll do today, is to derive the heat equation, which is the differential form of heat transfer. So look down at the paper and we'll get started. Set my stopwatch there. Okay, this is the geometry we're considering. It's a rectangle. We'll assume it's insulated on the top and the bottom. Okay? We'll call this TS1, just the temperature of that surface 1, and we'll call that one there TS2. Okay. And also we'll assume that this is the X direction, and assume coming out of the page is the Z direction. Okay. So if we look at a point in this material, we'll just look at a differential volume here. And this differential volume has a length of delta X and delta Y. Okay? So if we pulled this differential volume out and looked at the energy going into it, at the very center here we'd have X and Y. Over here we'd have heat coming out. We'll just call it Q dot at X plus delta X over 2. And on the left side of the page we'd have heat going in. We'll call that Q dot at X minus delta X over 2. Okay, so if we wrote the first law for this differential volume, that would say energy stored is equal to energy in minus energy out. Okay. Minus energy out. Okay. That's a true statement. Alright, so energy stored, what is that? Okay. Okay, the energy stored, we can define that as mass times the change in internal energy with respect to time. Okay? And the mass can be rewritten as density times volume. And for this object here, we're talking about delta X, delta Y, and delta Z. Okay? And if you recall from thermo, delta U, the change in the internal energy of a material, if it's incompressible, we can write delta U as the specific heat times delta T. You may remember that from thermo. The change in internal energy, delta U is equal to C delta T. Okay? So if we substitute these two things back into the energy stored, here's what we have. Energy stored is equal to mass, which is density, times delta X, delta Y, and delta Z, times C delta T divided by little delta T, which is the change in temperature. So this is change in temperature with respect to time. Okay? So that's energy stored. Okay, what about energy in? Well, let's look at that one. Okay, energy in. energy in is Q dot at x minus delta x over 2. And that's equal to, if we use a Taylor series expansion, that would be equal to Q dot at x minus the change with respect to x of Q dot times the distance we moved, which would be delta x over 2. Now that's the Taylor series expansion. You guys covered that in calculus. There's some other terms out here, higher order terms, but we will neglect those. And you can do that whenever delta x is small. Okay? So one more thing we'll do with this equation is for Q, right here, we're going to use Fourier's law of conduction, which of course you know is minus K times the area times delta T delta X. So if we substitute, what we would have is Q dot at x minus delta x over 2 is equal to Q dot at x minus the change with respect to x, and here's where we throw in Fourier's law for the Q dot here. That'd be minus K times the area, which would be delta y delta z, okay, times the change in temperature with respect to x, that's Fourier's law, and then times delta x over 2. Okay, if we did the same thing on the right side of our control volume for Q dot at x plus delta x over 2, if we did the same thing here, what you would get is energy out, and that is equal to Q dot at x plus delta x over 2 will be equal to Q dot at x plus the change with respect to x times the minus K, the area delta y delta z times the change in temperature with respect to x times delta x over 2. Okay, so now if we take all three of these terms here, energy stored is equal to energy in minus energy out. If we take those terms and substitute them into the heat, back into the first law, let me get this right here. This is what you'd get. First of all, energy stored. All right, energy stored. Let's see here. Okay, energy stored. What did it come out to be? Came out to be density times delta x, delta y, delta z times the specific heat times the change in temperature with respect to time, and all that was equal to the energy going in, which we saw energy in was this one. So that would be Q dot at x minus the change with respect to x. Let's see here, energy in. Okay, minus K times dt dx times delta y delta z times delta x over 2. Okay, then minus the energy going out, which we just saw is equal to Q dot at x plus the change with respect to x times minus K dt dx delta y delta z times delta x over 2. Okay, and we can simplify this down further. If you do some more algebra here, we can divide the volume out, delta x, delta y, and delta z. So if you do that, it all goes out with all of them here. And in the end, oh yeah, and Q dot x, that one goes out with this one. So in the end, what you have left is the density times the specific heat times the change in temperature with respect to time is equal to the change with respect to x of k dt dx. Okay? So this is the heat equation for one direction, x, one dimension. I mean, for example, you can simplify this further. If the problem is steady, nothing's changing with time. So for steady, that will go to 0. And then you just have temperature as a function of one parameter or one variable, so we could change these partial derivatives to ordinary derivatives. And then in addition, if your k is constant, you could pull that out. So for this special case, what we would have is this right here. Two derivatives of temperature in x, so you know you would need two boundary conditions to solve this problem, because you would integrate twice and get two constants. Okay? So that's the heat equation in one dimension. Now if we repeated that same thought process for three dimensions, delta x, delta y, and delta z. Let's see here, y, z. This is what you'd have. Here again, this is q dot at x plus delta x over 2. Q dot at x minus delta x over 2. Let's see here. Up here we'd have q dot at y plus delta y over 2. And down here we'd have q dot at y minus delta y over 2. And then, here again you can do the same thing in the z direction. And you get q's in the z direction. Okay, if you applied that same thought process to this three-dimensional cube, what you would get is something known as the heat equation. And it looks like this. The heat equation, you have, hope I can get it all on here. The change with respect to x times k times dt dx plus the change with respect to y times k dt dy plus the change with respect to z times the k dt dz plus, now just in general, we'll throw one more thing in here. You may have some generation, so we'll call this q dot gen. For example, current through a wire is going to generate heat. Well, this would be your generation right here. And all that's equal to the density times the specific heat times the change in temperature with respect to time. Okay? So this is the heat equation for three dimensions. Now you're looking at that thinking, I can't solve that. Well, what we'll do in class, if you want an analytical solution, you'll have to make enough assumptions so that you can cancel off enough of these terms to get it down to something more manageable form that we can actually integrate. If you can't do that, if the conditions won't allow you to make those assumptions, what you would have to do is resort to numerical schemes to solve this equation. And there's software out there that will do it. So that's going to be it for the heat equation. Let's see here, we're having technical difficulties. In the next video, I'm going to show you how to come up with your boundary conditions. It'll be real short, but I'll show you a few boundary conditions that are typical. Alright, see you later.